is our last lesson here in chapter 9. I don't even remember what we're doing after this, so I got no words for that. But today we're talking about symmetry. We are specifically talking about line symmetry and rotational symmetry. And point symmetry, I really just think is the same thing as rotational symmetry. So I'm not really going to address it because it's not necessary, really. One gets the other. So, line symmetry. A figure has line symmetry if the figure can be mapped onto itself by a reflection. Think about a mirror image. So, when you're asked, does this have line symmetry, or how many lines of symmetry are there, you get to ask yourself, hey, if I were to put a mirror somewhere on this figure, would the one side be a mirror image of the other? And so on this particular figure, if I were to place a mirror on this line, it exactly cuts the figure into two mirror images. Does that make sense to you? All right, so one side is the mirror image of the other. So that is line symmetry. Now, rotational symmetry is when a figure can be mapped on itself by rotating the figure less than 360 degrees. So on this particular figure, it has rotational symmetry because you can imagine that if it were spinning, much like a pinwheel might, okay, if it were to spin, would it map onto itself? Okay, it would look almost identical. So imagine this point on the sun rotating a little bit, and if it were to line up with this point, would it look identical to where it started? Okay, and so how many times can we do that? In Delta Math, it's going to ask you what it's how many degrees the rotational symmetry is going to be, and that's pretty easy to figure out. You can imagine we could keep rotating, and anytime one of these points were to line up, then it would map onto itself. So how many points do we have here? 1, 2, 3, 4, 5, 6, 7, 8, I think would do it. And so how many degrees are there in a circle? 360, yeah. So we can take 360 degrees and divide that by our 8 points. And will someone math that for me? 45. Okay, cool. So then this would have rotational symmetry with a minimum degree of 45 degrees. Okay. And so that's the kinds of questions we're getting asked today in Delta Math, which is pretty good. So think about a pinwheel spinning, and all you have to do is figure out, how many degrees does it have to rotate so that it lines up with itself again. So a few examples here. Determine if the figures have line, point, or rotational symmetry. And again, I don't care about point symmetry, so I'm not even really going to talk about it because it is really just rotational symmetry. Check all that apply. So number 1, is there symmetry around a line? Yeah, for sure. So the question then is, we need to know the line. So in Delta Math, they're going to have you draw the line. Okay. And so where's the first line? From the top and like straight down? Yeah, a vertical line through. All right, so there's one line of symmetry where the left side is a mirror image of the right side. Is that the only line? No, cross. Okay, so we could go this way too, so horizontally. So now the top is a mirror image of the bottom. That's true. Is that the only way? Diagonals. Yeah, we absolutely could do diagonals here. So right here, now you see this side is a mirror image. Yeah, is there another one? Yeah, the other diagonal, yeah. So, and here again, we have a sort of top half as the mirror image of the bottom half. You can imagine if you were to fold that figure on those lines, they would perfectly line up, okay? So how many lines of symmetry do we have here? 4. Okay. So again, I'm not talking about point symmetry. Does this figure have rotational symmetry? Yes, it does. And so again, how do we figure out the rotational symmetry? So you can imagine if it's spinning like a pinwheel, I'm going to just take like a corner, vertex here, and if I rotate it and that corner lines up on top of itself, then it would have rotational symmetry. Well, how many times can those corners line up? Well, how many? 1, 2, 3, 4, 5, 6. Or six little corners that could match up, yeah? Oh. Yeah? So for the rotational symmetry, we would have to take 360 degrees and divide by those 6 little, which is 60 degrees. So we have 60-degree rotational symmetry there. Okay? And again, write this down because you have to do these things on Delta Math. All right? Won't hurt though. Number 2, does it have line symmetry? Yeah. How many lines? One, huh? Just one? You can go from each little vertex here, from this corner here as well. You see that we have 2 mirror image sides. Again, imagine folding that triangle along that line, and they would exactly match up.
Like, can we go across?
Directly in half this way, horizontally? Would it fold on top of itself? If you drew that line in, would that point line match up with the other end?
I mean, it could. No. Oh, wait.
And so this one, if we go from this point, again, that sort of, this top side would exactly fold up with this side. So there are 3 lines of symmetry in this triangle, okay? What about rotational symmetry? Imagine right in the center, could you rotate this triangle where it would look identical? You don't think so? You couldn't rotate that triangle?
I mean, it'd still be a triangle no matter how many ways you rotate it. It'd be on its side and be upside down.
So, but this looks like appears to be an equilateral triangle. Oh, okay. So, like, if you took this point and rotated it, would you be able to tell that it's a different triangle, or would it look identical to what we started with?
It looks identical.
Okay. So we can rotate this 1, 2, 3 times around there. So it does have rotational symmetry. So 360 divided by those 3 little points that we could land on, and we get 120-degree rotational symmetry. Okay. Number 3, does it have line symmetry?
Yes. No, it doesn't. Well, yes, it does. It does. Yes, it does. Yes, it does. It has.
So you think that if we go like from this corner to this corner?
Yeah.
Okay.
Both corners.
So interesting. Okay. So imagine if we did this line right here, okay, and you were to fold it. Do you think those corners would match up? So you would have, this corner would fold, and it would sort of, like if you were to fold this top side over, it would look kind of like this, if you were to fold it over. It would not, those 2 points don't match up with one another.
But that, because they turn into 2 little triangles. The 2 little triangles go.
No. 2 different size triangles, so they're not the same.
It's a parallelogram.
Let's make a picture here. Let's see. So I'm gonna try here. There we go.
I'm too smart for you. That's why.
I get it.
I get the flag. You've been hypnotized by the boys' laugh.
All right, it's not a perfect match, but I think it's good enough. All right, when in doubt, make a model. So here we go, parallelogram-esque shape. Let's see, if it has line symmetry, you think we can fold it from one corner to the other. See what happens here. So I gotta like go right and split that. This is really hard to fold. Right to the corner. We might have to use our imagination a little bit here. Let's see. Oh, there you go. So does it match up with itself? Oh, I missed a little bit. It's not perfect. Okay, so here we have our line right from corner to corner, and you can see that these two other points don't match up with each other. All right, you see that? They don't really match up. So can I go the other way? Can I line up this corner to this corner like that to make those corners match up? Well, then I'm clearly like that. This doesn't map. It doesn't match up with itself. Like there's this. It's not the same. Okay. So you can see that doesn't quite work. So that one doesn't have any line symmetry. Okay. Takes a little bit to figure that out. So it does not have line symmetry because it wouldn't fold onto itself, okay? Does it have rotational symmetry?
No, it doesn't have line. It doesn't have line. It doesn't have rotation.
Really? That's what you believe?
It's got 4 corners. So every time we had rotational, we always had the line. So I'm putting one and one together. My bad.
So again, if you think about spinning it like a pinwheel, all right? So if I take and have right here in the center and I spin this corner, now I can't just spin it to this corner, that wouldn't match up, but I could go over here to this corner, all right? I could spin this figure a full 180 degrees and it looks identical to how we started. Does that make sense to you? Okay. So this one could spin from this longest corner all the way to the other longest corner. It has rotational symmetry. In this case, that would be 360 degrees. We've got 2 points that we could use to rotate to themselves. And so that would be 180 degrees for rotational symmetry. What about number 4? Does it have any line or rotational symmetry? No. None. None on that one. Number 5. Okay, it has. All right, let's start with rotational since that came up first. So it does have rotational symmetry. What's the minimum degrees for rotational symmetry? 360. Minimum. We want the minimum number of degrees. So yes, I could rotate a full 360 degrees. Every figure can rotate a full 360 degrees and map onto itself. That's true. But it has to be less than 360 degrees to be rotational symmetry, okay? So how many degrees do I need to rotate that star so it looks identical?
72.
How'd you get 72? Yeah, so I can take this point and rotate it right there, and that star would just rotate and look identical to what we started with, like you wouldn't know you did it, okay? Again, there are 5 points on this star that we could rotate to, and it would look like exactly what we started with every single time. So it does have rotational symmetry, 360 divided by 5 points that could match up, and that gives us 72 degrees. What about the line symmetry? Does it have line symmetry? Yeah. Does have line symmetry. Again, imagine folding this star right through vertically. And again, these little points, they would fold right on top of each other. On all those things would just fold and match up real good, yeah? Okay, is that the only place? Absolutely. So there's that line, but any of these points could go from the point to what I'm going to call the crotch of the star. That's awesome, right? Again, it is, you've got this top side of the star that would exactly fold over onto that bottom piece. And again, from each little point to each crotch. All right. I don't know the better way to say that. Like, it just doesn't, that's all I got. All right. So let's see. It looks like I've got 1, 2, 3, 5 lines of symmetry? Yeah? Okay. 5 lines of symmetry. All right. What about number 6? Does it have line symmetry? So it would fold, if you drew a line, it would fold onto itself exactly. No. Like if I did a vertical line, they miss each other. One folds up high and one folds, yeah? Okay. Same thing here. If I go horizontally, they would fold, but they would miss each other. One would be here, this little thing would be on the left, and this one would be on the right side, so they don't match up. So it doesn't have line symmetry. What about rotational symmetry?
Yeah.
Yes. Again, here's the point. And imagine, can you spin it and it will look identical? Imagine taking this corner and spinning it over so it lines up with this corner. Would that work? Yeah. So that is 360 degrees divided by those 2 points that we could match up. 180 degrees. So that's technically point symmetry, but it's still just rotational symmetry. What about number 7? What's it got? Line symmetry. Yeah, they're right down the middle. It does have line symmetry. Any other lines of symmetry or just the one? Just the one. Yeah, that's it. That's all it's got. What about number 8? Does it have any symmetry? Nada. No, nothing. Okay. Turn the page. This is a lot, right? Let's see. I don't want to do all of these, but I do want to hit up some good ones here. So number 9 looks like a pinwheel. Does it have line symmetry? So again, imagine drawing a line, but it has to fold exactly onto itself. No line symmetry. What about rotational? Yes, it does have rotational symmetry. And so again, if you take a point and rotate it, then those would look identical to how they started. So how many degrees do we get if we... Okay, so 360 divided by 4 would be 90 degrees for that minimum rotational symmetry. Okay, number 10, line symmetry? Yeah, how many lines of symmetry do you think? 2, good, yeah, we have vertical. So again, those 2 sides would fold exactly onto one another, and a horizontal line, and again, those 2 flaps would fold exactly up towards one another. So 2 lines of symmetry. What about rotational symmetry? Does it have that?
Yes.
So again, if you imagine it's got a center point that it's spinning on, and again, we can take a corner and I can rotate it. Can I rotate it just to here? No, I have to rotate it over to here, and that would map, and the picture would look exactly the same. So, and that would happen. I could do that rotation 2 times. So 360 divided by 2 is 180 degrees for the minimum rotation to map onto itself. Let's see. Let's go look at number. Let's just do. Well, let's do 13, I guess. What does it have? Line symmetry? How many lines? 3? Yeah. It does have 3. You can imagine, right? Vertical, those petals would all fold right up. And we can do that through each little petal. You can draw those lines right through the center of the petal. Those other petals would match up, and it would fold right in half on each petal. That's pretty good. And what about rotational symmetry? Yes, so how do we figure out that rotation? 360 divided by 3, very good, which is 120 degrees. Awesome. Okay, and then of course there's like the snowflake down here, which I think is really, really cool. It also has a lot of symmetry going on in it. But be careful, it does take a little bit of time. A lot of line symmetry and rotational symmetry for both of these. Pretty interesting. Do you guys have any questions for me? Sweet. Exactly 20 minutes.